Okay, so for this video, we're actually just going to kind of, I guess, go over some ideas of the whole stoichiometry when it comes to these enthalpy reactions. And so the first thing that you have to kind of understand is that most of the time, whenever you see these reactions, you might see some fractions kind of involved in there. And so very simply, let's kind of go back to our normal water. And so if we normally write out the chemical reaction for water, we would write out as 2 H2s plus an O2 will produce 2 H2O. But as you can see here, whenever we create this, we're actually forming 2 molecules of water. And so whenever you see these enthalpy reactions, especially when we start talking about the enthalpy or formation reactions, these are typically going to be talking about the energy required or the energy that's released whenever 1 mole of the substance is being produced. And so instead of actually seeing this chemical reaction run out as 2 H2s plus O2 gives you 2 H2O, typically you won't really see it as in 2 moles of H2O. You'll see it in terms of 1 mole of H2O. And so because of that, what you're going to have to do is kind of go through and adjust some of these coefficients. And so you actually end up with half of a mole of O2 in order to, again, produce this 1 mole of H2O. And so if you kind of go through and look at any chemistry book that has all these values written out, you'll see that the formation of H2O is going to have an enthalpy related to it as negative 285.8 kilojoules per mole of the substance. And so the first thing you have to kind of understand here is that whenever we take 1 mole of H2, half a mole of O2 to produce 1 mole of H2O, this delta H is going to be a negative value. And so that this is stating that this chemical reaction here, or this process of forming this water, is going to be an exothermic reaction because we're looking at a negative delta H. And so when we kind of go through and start manipulating these equations, the one thing you have to understand is that if you manipulate anything inside of the balanced chemical equation, you have to do the same thing to the delta H. And so in order to make this a little less complicated or a little bit more simplified, you have to kind of think of this value, this negative 285.8, as nothing more than just a coefficient for your delta H. The same way that we can imagine that there is a 1 in front of that H2, there's a half in front of that O2, and there's a 1 in front of this H2O. We can just imagine that there's a negative 285.8 in front of this delta H. This delta H is, again, just another step or another, I guess, constituent of this chemical reaction. And so when we kind of go through and look at this, this is nothing more than just the expanded balanced chemical equation. And so the same exact way that having a balanced chemical equation of just this information right here tells you that you have 1 mole of H2, half a mole of O2, 1 mole of H2O. All that this really is doing is just expanding that information given by that chemical reaction. And so here it's telling you that there's 1 mole of H2, half a mole of O2, 1 mole of H2O, and negative 28 or 285.8 kilojoules of energy associated with this chemical reaction. And so, same exact idea that we've kind of mentioned in the past. Say that we want to go back to our original equation when we had our 2 H2s plus our 1 O2 to produce our 2 H2Os. And so the reason why I kind of changed this equation to this in order to illustrate this delta H is because this delta H, as I stated, is per mole, or again, it's 1 mole of this stuff. And so again, this is again kind of redundant here. But then this negative 285.8 kilojoules is associated with that 1 mole of water. And so when we kind of go through and look at this, if we double all of our coefficients here, or make this 1 go to a 2, this half go to a 1, this 1 go to a 2, and you do the same thing with our delta H. And so in this situation, if we're kind of going through and looking at all this, you would have to do the same thing. So this would come out, I didn't multiply this earlier, 285.8 times 2. And again, you would end up with negative 71.6 kilojoules of energy associated with this here. And so we kind of go through and actually look at the other half of this. Say we don't want just 1 mole of this stuff. If we want half of it or anything like that, then we would do the same thing with the delta H. On the other end of this idea is, say that we're not interested in forming water, we're interested in decomposing water. And so say instead of taking our H2 and we're adding it to O2 to produce our water, we want to go the other route. And so say that we want to have our 1 H2O, so our H2O decompose into our H2 plus our half of our O2. And so, because we're now going in the opposite direction here, we have to understand the fact that we are looking at opposite kind of reaction occurring. So if this reaction, going the way that I wrote it, H2 plus half O2 gives you H2O, is an exothermic reaction, the other way has to be an endothermic reaction. But luckily for us, if you go one direction or the other, you're still going to be looking at the same amount of energy being absorbed or released. The main idea here is that this case, you're looking at energy being released absorbed instead of being released. And so, you kind of go through and whenever I say manipulate these equations, as I state in my slides, this is all I'm really talking about, is just kind of going through and just changing the coefficients or changing the way that it's written. This can become a little bit more important when it comes to actually kind of working out these problems in the later on steps here. And so, when we kind of go through and kind of keeping the same idea here, let me get rid of all this stuff. So, using this material or using this idea, we can actually go through and start working out some actual word problems here. And so, if you have a balanced chemical equation, it can be manipulated, it can be used the same exact way as any other balanced chemical equation in the past. Now we're just dealing with some additional information here. And so, say that a problem occurs in which we have 12 grams of H2, and we are going to react it with 76 grams of O2. And so, one of the first things you should probably understand, hopefully by now, and again, if I were in class, I would be jumping up and down yelling at you guys. But if I give you information about H2 and O2, you need to realize that both of those are reactants. And as I've mentioned several times during lecture, if you have information about more than one reactants, this is now a limiting reactant problem. And so treat it the same way you've treated all the other limiting reactant problems. You have to convert both of your reactants into a common product. Just in this case, your common product is going to be delta H rather than an actual chemical compound here. And so going through the same steps we've done multiple times in the past, we're going to convert our grams of H2 into moles of H2. We know that 1 mole of H2 is 2.02 grams of H2. And by using our balanced chemical equation, we know that 1 mole of H2 is always going to, again, be associated with this negative 285.8 kilojoules of energy. And please notice, all I'm doing here is just using my balanced chemical equation the same way I would do in the past. And so whenever I plug all this into my calculator, I get negative 1698 kilojoules of energy. Doing the same thing with my O2, treating it the same way that you would with any other limiting reactant problem. You know that our 1 mole of O2 is going to be 32.00 grams of O2. And then convert our moles of O2. Convert our moles of O2 into kilojoules using the same balanced chemical equation. We know we have negative 285.8 kilojoules for every half mole of O2. And so when you kind of go through and do this calculation, I end up with negative 1358 kilojoules of energy. And so one thing I do have to kind of point out about this answer in respect to all the other limiting reactor problems that we've done in the past is, remember, this negative sign is just telling you that if it's going to be if the energy is going to be released or if it's going to be absorbed. And so this negative here is just going to tell you the direction in which this energy is going. And so if you're doing a limiting reactant problem here, you're still going to be looking at the less of the magnitude of the energies, not the actual signs that are associated here. And so in these two cases, your negative 1358 kilojoules is going to be the lower the magnitude of the energies, or this is going to be basically your theoretical yield when it comes to energy associated with all this stuff. And so when it comes to enthalpy of reactions and coming to terms with stoichiometry, do not overthink these. Do not think about it any more than the same exact way you've thought about these limiting reactant problems in the past. The same exact stoichiometry, same exact setup, everything still is exactly the same. You're just now using kilojoules instead of moles of something.